All right, welcome back to the deep dive. We're kicking things off today with a quote that's almost 800 years old from St. Thomas Aquinas. But believe me, it's shockingly relevant to the data systems we're all wrestling with today. If the highest aim of a captain was to preserve his ship, he would keep it in port forever.
It's a profound thought, isn't it?
Yeah.
It really challenges our basic assumptions.
Yeah,
For us today, this deep dive isn't just about understanding how data systems are currently built. It's about envisioning how they should be.
right.
Our mission is to explore how to design applications that aren't just reliable, scalable, and maintainable. Those are, almost yesterday's goals, but also truly robust, correct, evolvable, and fundamentally beneficial to humanity.
That's our North Star for this deep dive for you. We're going to cut through some complex concepts that often feel like a tangled mess. We'll untangle the dizzying world of data integration, explore how to ensure your systems stay correct even when the world throws a wrench in the gears, and then, crucially, confront the ethical responsibilities that come with wielding such powerful, data-intensive applications. Get ready for some serious aha moments. So, let's jump right into the first big puzzle, data integration. You might think, okay, I just want to store some data and look it up later, and there's like one perfect way to do that.
Right.
But the truth is, there isn't one right solution out there. What have you found makes this problem so nuanced?
Well, it's all about context and usage patterns.
Mhm.
For any given data problem, there are countless approaches, each with unique strengths and weaknesses tailored to how you're going to use that data. And that brings us to a really tricky part for you. The person trying to choose the right tools, software vendors. They're usually not incentivized, let's be honest, to tell you when their product isn't a good fit for your specific needs.
That's a good point.
Our goal here is to arm you with the questions to ask so you can kind of read between the lines and truly understand the trade-offs.
Even if you're a wizard with every single tool, the reality of complex applications is that data gets used in so many different ways. It's not just sitting in one place.
Exactly.
This inevitably means you're going to end up, cobbling together several different pieces of software. Think about it. A primary database, maybe a full-text search index, analytics systems, caches, machine learning models, even notification systems. It's a lot.
It's true. The sheer range of things you might want to do with data is dizzyingly wide. Each of those uses often demands a different representation or access pattern for the same underlying information.
Right.
And as those data representations multiply across your system, the integration problem just gets harder and harder.
Yeah, I can see that. Imagine your favorite online retail site. Your order details are probably in one transactional database.
Sure.
But that same data is also likely in a search index for quick product lookups, an analytic system for sales trends, maybe a cache for frequently viewed items. Keeping all those copies consistent, that sounds like a Herculean task. How do we even begin to tackle that?
That leads us straight to a really powerful solution. The principle of deriving data. Instead of trying to write the same new information to multiple systems all at once,
Okay.
you first write it to a single system of record database. Then changes from that primary source are captured, maybe using something called change data capture or perhaps an event sourcing pattern.
Right.
And those changes are then applied to all your other derived systems like that search index in the exact same order.
So, if I'm hearing this right, the absolute core insight for building robust data systems isn't just about speed. It's about establishing one single truth for the order of operations. That's the secret sauce for preventing permanent data chaos and making recovery painless. That's a huge takeaway.
Precisely. This approach funnels all user input through that single system, establishing a definitive order for writes. That's crucial because it prevents different parts of your system from making conflicting decisions about concurrent writes, which is how systems can become, permanently inconsistent. Plus, when updates are deterministic and idempotent,
Meaning you can run them again without messing things up.
right, applying them multiple times has the same effect as applying them once. Fault recovery becomes so much easier. You just reapply, no worries.
That makes a lot of sense for a single source. But how does this derived data approach stack up against the classic way of ensuring consistency, which is distributed transactions?
Well, I think at an abstract level, both aim for consistency, sure, but their methods are quite different. Traditional distributed transactions, like we call two-phase commit or 2PC, essentially work like a very strict group agreement. First, all participants say they're ready to commit a change that's phase one, Only if everyone agrees do they all then actually apply the change simultaneously. That's phase two, the atomic commit.
Right. All or nothing.
Exactly. If even one participant can't get ready, the whole thing rolls back.
And I know distributed transactions often promise linearizability, which is a very strong guarantee, like reading your own rights immediately. That sounds appealing, doesn't it?
It does sound appealing, but the trade-offs are significant. Distributed transactions, particularly something like XA, which is a very strict, traditional way of coordinating across different databases, often suffer from really poor fault tolerance and performance.
Yeah, I've heard that.
Imagine trying to get 5 different chefs, each with their own kitchen, to perfectly coordinate one dish down to the millisecond. If even one chef hiccups, the whole meal gets thrown out. That's that amplification of failures we mentioned earlier.
Right.
Derived data systems, by their nature, are often asynchronous. This means they don't offer those same strong, immediate timing guarantees by default.
So given those trade-offs, where does the balance lie? What's the better path forward usually?
Well, in the absence of widespread support for a better, more robust, distributed transaction protocol, log-based derived data is really emerging as the most promising approach for integrating diverse data systems.
Okay.
Even if it means initially accepting asynchronous updates, it provides a much more robust and scalable foundation. And we can actually build stronger consistency guarantees on top of these asynchronous systems, which we'll touch on later.
Okay, so while a totally ordered log sounds fantastic for maintaining consistency, it definitely hits some limits, especially as systems grow. We run into scalability bottlenecks pretty quickly, right?
Absolutely. For smaller systems, sure, a single leader can easily churn out a totally ordered event log. But when you hit a certain scale, that single leader inevitably becomes a bottleneck for throughput.
Just can't keep up.
Right. And if you partition the log across multiple machines to handle more events, well, the order of events across different partitions becomes ambiguous. It's kind of like having multiple lanes on a highway. You can go faster, sure, but you lose that strict single-file order.
And geographical distribution adds yet another layer of complexity, I imagine.
Exactly. If your servers are spread across multiple data centers, you typically run a separate leader in each location just to compensate for network delays. That means events originating in different data centers have an undefined order relative to each other. And, modern architectures like microservices, where each service manages its own state, and even clients with offline capabilities, all contribute to scenarios where a single global order simply isn't feasible or maintained.
This brings us to a fascinating and, frankly, a bit spooky problem I read about called lost causality. It sounds almost philosophical. Can you help me and our listeners grasp this with a concrete example? Where does this subtlety usually bite engineers?
It's a great question, because it is subtle but so impactful. Okay, imagine a social networking app. A user unfriends someone, then immediately sends a message to their remaining friends complaining about their ex-partner.
Okay, classic scenario.
Right. The intention, obviously, is that the ex-partner shouldn't see the message. But if the system stores friendship status in one place and messages in another, and the causal link, the fact that the message was sent after the unfriend event, is lost across those systems, the notification service might process the message before the unfriend. Result: the ex-partner incorrectly receives the message. It highlights how even subtle dependencies can be missed without really careful handling.
Wow. So how are we tackling these increasingly complex ordering challenges when a single global order isn't always possible or practical?
We're seeing a lot of work in areas like logical timestamps. These can provide a kind of total ordering, though they require recipients to gracefully handle out-of-order delivery. Also, unique event identifiers that explicitly record causal dependencies are proving to be very promising. Now, conflict resolution algorithms can help maintain state consistency, but they can't magically undo external side effects like, say, an unwanted notification being sent.
Right, the damage is done.
Exactly.
Right.
That's why prevention, or at least acknowledging causality, is key.
So we've established that derived data is a powerful path to consistency, but how do you actually build and maintain all those derived views? That's where the workhorses of modern data systems, batch and stream processing come in. They're sort of the engine room for these ideas.
Absolutely. These processors are the essential tools for transforming, joining, and aggregating data to produce all those derived data sets we're talking about, whether it's a search index, a materialized view, or even your personalized recommendations. And what's truly interesting is how the traditional distinction between batch processing, which deals with finite chunks of data, and stream processing, which handled unbounded, continuous data, is really blurring. Modern systems are increasingly emulating one on top of the other.
And the material points out that these systems encourage deterministic pure functions. Why is that such a big deal? What's the benefit there?
Well, it's not just good for fault tolerance, because it makes operations idempotent, like we discussed.
Right.
It also vastly simplifies reasoning about complex data flows.
Hmm.
And the asynchronous nature of stream processing is key here. It makes systems inherently more robust, because faults tend to be contained locally. This is
Oh.
a stark contrast to those distributed transactions we mentioned, which tend to amplify failures, potentially bringing down large parts of your system if one tiny piece hiccups.
Right, the cascading failure problem.
Exactly.
Now, one of the most powerful aspects of this derived data approach, especially with these processors, is how it enables application evolution, particularly through reprocessing.
Yeah.
This sounds crucial for long-term system health.
It really is. Stream processing gives you those low latency updates for immediate changes, which is fantastic for real-time needs.
Hmm.
But batch processing allows you to reprocess all historical data,
The whole history.
the whole history. This is absolutely key for application evolution and supporting new features because it lets you effectively restructure a data set into a completely different model without losing any information.
This brings to mind a fantastic real-world analogy I read about 19th century railway gauge changes. It's such a brilliant parallel.
It really is. Imagine needing to convert an entire railway network to a new standard gauge without shutting down all traffic. It sounds impossible, right?
Yeah, how would you even do
The
that?
solution was brilliant. Gradually add a third rail, creating dual gauge tracks. This allowed both old and new trains to coexist and operate simultaneously during the transition.
Ah, clever. So just like those railway tracks, derived views allow you to maintain old and new schemas side by side. That's incredibly powerful for flexibility.
Precisely. This significantly reduces risk and enables gradual, reversible migrations. If something goes wrong with a new schema or a new view, you always have the old working system to revert to or run alongside.
Makes sense.
This kind of flexibility makes you more confident about going ahead with changes, and thus you can often move faster to improve your system. It's a powerful idea for data system evolution, transforming what could be a huge, risky Big Bang migration into a series of smaller, safer steps.
Speaking of influential ideas, the Lambda architecture certainly made waves a few years back. What was the core concept behind it?
Right, Lambda. The idea was you'd record all incoming data as immutable events, kind of like event sourcing.
Okay.
Then you'd run two parallel systems, a batch processor, maybe like Hadoop MapReduce, and a separate stream processor, like Storm or Flink. The stream processor would quickly produce an approximate update for immediate use,
For speed.
while the batch processor would later consume the same events to produce a corrected, more accurate version of the derived view.
It sounds clever on paper, trying to get both speed and accuracy. But I remember hearing about some significant practical pain points. Where did it stumble?
You're right, the theory was appealing, but the practical problems were substantial. First, maintaining the same exact logic in two completely different frameworks, one for batch and one for stream, required significant extra effort. It was complex to develop, test, and debug.
Double the work, basically.
Pretty much. Second, merging the outputs from these two separate pipelines could be a real headache, especially for more complex aggregations or calculations. And finally, frequently reprocessing large historical data sets for the batch layer was expensive,
Yeah, I bet.
which ironically led to people introducing incremental batches, which just made the batch layer more complex and kind of defeated some of the original simplicity goal.
So what's the current thinking? Is there a way to get the best of Lambda without its downsides? Have we moved beyond it?
Absolutely. Recent advancements really focus on unifying batch and stream processing by implementing both computations within the same system.
Ah, okay. One engine.
Exactly. This relies on key features becoming more widely available. The ability to replay historical events through the same processing engine, exactly one semantics, for stream processors, which is a huge deal for correctness.
That's crucial.
And the really important concept of windowing by event time rather than processing time, that's essential when you're reprocessing historical data to get accurate results. This truly brings the best of both worlds together, offering both speed and accuracy in a single, more manageable system.
Okay, let's shift gears a bit and talk about something truly philosophical in data systems, unbundling databases. It almost sounds like this tension between, say, the Unix philosophy and the traditional relational database philosophy.
It really is a philosophical tension. Think about Unix.
Hmm?
It aimed to provide a low-level abstraction to hardware with simple interfaces like pipes and byte streams. Small tools doing one thing well.
Right, compose them together.
Exactly. Relational databases, on the other hand, try to give application programmers a high-level abstraction, hiding all the messy complexities of disk structures or concurrency, offering neat things like SQL and transactions.
Hmm.
The NoSQL movement, in a way, is applying that Unix-esque approach of low-level, composable abstractions to the world of distributed data.
And out of this tension emerges a fascinating concept, the metadatabase. How does that reshape our perspective? What does that mean?
It suggests viewing the entire data flow across an organization as effectively one huge database.
Oh, okay.
In this light, batch and stream processors aren't just separate tools.
Yeah.
They act like elaborate implementations of triggers or stored procedures or materialized view maintenance routines that you might find inside a traditional database.
Right.
And all those derived data systems, your search indexes, your caches, are simply different index types within this larger metadatabase. So
Yeah.
it's a very holistic way of looking at data flow across the entire org.
So if we accept this meta database idea, how do we compose these diverse systems? I understand there are two main paths: federated databases and unbundled databases. Can you break those down?
Exactly. So federated databases focus mainly on unifying reads. They provide a single query interface over diverse underlying storage engines, like PostgreSQL's foreign data wrapper is a good example.
Okay, so reading from different places through one lens.
Precisely. Great for combining data for reading.
Mm.
Unbundled databases, however, focus on unifying writes. This is about taking a database's internal features, like index maintenance, and unbundling them to synchronize writes across disparate technologies,
Okay.
often using change data capture and event logs.
Oh, okay.
It beautifully aligns with that Unix philosophy of small tools that do one thing well, communicating via simple, uniform APIs, which in this case are those event logs.
And it seems unbundling wins for writes because it tackles what's been called the harder engineering problem. Why is that? What makes it harder but maybe better?
It offers something crucial: loose coupling. This makes systems more robust to outages because individual components can fail without necessarily bringing down the whole interconnected system.
Right, containment.
Exactly. And, crucially, it allows different teams to develop independently, which is huge for organizational scalability. It prevents one team's choice of database technology from becoming a bottleneck or a tight coupling point for everyone else downstream.
So does this mean we should just throw out traditional databases entirely? Is that the message?
Oh, not at all. Not at all. It's really important to stress that unbundling doesn't replace databases. They're still absolutely vital for maintaining state, maybe in stream processors, and certainly for serving queries efficiently.
Okay.
The goal of unbundling is more about breadth, not depth. It's about combining several different specialized databases or systems to achieve good performance for a wider range of workloads than any single system could possibly handle well on its own. If one technology happens to satisfy all your needs, absolutely use it. Unbundling is for when no single piece of software really satisfies all your requirements effectively.
It sounds like we're still missing a critical piece of the puzzle, though, for this unbundled vision to truly take off easily.
We are. I think what's still needed is the unbundled database equivalent of the Unix shell. A high-level declarative language for simply composing these storage and processing systems together.
Like a command line for data flow.
Exactly. Imagine being able to just type something like MySQL Elasticsearch and have it automatically set up the pipeline to index your database, continually capturing and applying changes without you having to write any custom integration code. That's the dream, really. It simplifies all the complex plumbing.
This whole idea of unbundling databases and using data flow leads to a fundamental shift in how we think about building applications. It's been called database inside out. What does that really mean?
It truly reframes our relationship with state, with data. Think about a spreadsheet for a moment. When you change an input cell, any cells that depend on it automatically recalculate.
Yeah, instantly.
Instantly. That's kind of the ideal for data systems. Change a record, and its index, its cache, or some aggregation automatically refreshes. Most mainstream programming languages are still, frankly, miles behind this kind of natural data flow programming capability.
So if our data is always flowing, how does our custom application code fit into this new model? Where does it live?
Our custom application code effectively becomes the derivation function for all sorts of things. Secondary indexes, full-text search capabilities, machine learning models, even UI caches. Now, databases historically struggle to host this kind of custom logic effectively or safely.
Right.
This new model beautifully separates those concerns. Durable storage in one place, the database or event log, and the custom logic running elsewhere, maybe as a separate service or process.
This separation of application code and state sounds almost like a functional programming mantra, like the separation of church and state, as the material puts it.
Precisely. It makes so much sense to have distinct parts of a system specializing in durable storage, our databases, our logs, and other parts specializing in running application code, managed perhaps by deployment tools like Docker or Kubernetes.
Okay.
The problem with traditional web apps, though, is that databases often act like passive variables. To see if something changed, apps often have to poll them, querying periodically.
Of asking anything new, anything new.
Exactly. Subscribing to changes is only just beginning to emerge more widely, but it's a real game changer for this data flow approach.
So data flow means moving beyond passive databases to a more active interplay and collaboration between state changes, and the code that processes them.
Yes, exactly. Application code responds to state changes happening in one place, but triggering changes elsewhere. And this leads us naturally to think about stream processors and services. They share the same organizational scalability benefits of microservices, due to loose coupling.
Right.
But their communication mechanism is fundamentally different. Asynchronous message streams versus synchronous request response, like REST or gRPC.
And this asynchronous data flow can be so much faster and more robust, right? It just makes intuitive sense, avoiding those tight couplings.
It absolutely can be. Think about something like currency exchange rates. Instead of your system constantly querying an external service for every single purchase,
Which could be slow or fail.
right? You could instead subscribe to a stream of rate updates and store them locally, maybe in a fast cache or a local database. Then when a purchase comes in, you just query your local copy. As the saying goes, the fastest and most reliable network request is no network request at all. It's like subscribing to a weather report instead of constantly calling the weather hotline. You get the updates automatically pushed to you, and when you need to know the temperature, it's already right there, locally. No waiting, no network dependency at that critical moment. That's the power of data flow.
And we can push this idea even further, observing derived state and extending it all the way out to the clients, to the end user's device.
Yes, we can clearly define the write path as the eager, pre-computed work-like updating an index when data changes, and the read path as the lazy work done on demand, like querying that index when a user asks for something.
Okay.
The derived data set is their boundary. It's a trade-off point between the work done at write time versus read time. And with modern clients, think JavaScript web apps, mobile apps that can maintain local state, and even work offline, we can truly extend that write path all the way to the end user.
How does that work?
Well, after an initial state synchronization, changes happening back in the system can be pushed directly to devices, maybe via WebSockets, drastically reducing staleness for the user. They see updates almost instantly.
And this is where it gets really cutting edge, this idea that even read requests can be treated as streams of events. How does that work? That sounds counterintuitive.
It's a fascinating concept.
Yeah.
You essentially send your read requests themselves as events onto a stream. Then you use a stream processor to perform a stream table join between this stream of requests and your database state, or rather a stream of database changes.
Wow, okay. What's the benefit?
This not only enables distributed multi-partition queries, which is a huge scalability win, but it also allows you to track causal dependencies. You can potentially reconstruct precisely what state a user saw before they made a particular decision, because their read request and the data state are flowing through the same ordered system. It's a fundamental shift in how we can design and understand user interaction with data.
All right, let's talk about aiming for correctness. When systems are stateful, they tend to remember errors forever, making correctness absolutely crucial, but incredibly difficult. Traditional ASA transactions, while useful, are actually often weaker than they seem, especially with common weak isolation levels people use.
That's a critical point. Even if a data system provides strong safety properties like, say, serializable transactions, it doesn't automatically guarantee your application is free from data loss or corruption if, for instance, you have a bug in your code that writes incorrect data. The database only guarantees consistency if the application correctly uses its features. It can't prevent application bugs.
This brings us to a really foundational concept, the end-to-end argument for databases. Can you break that down for us? What's the core idea?
This is a classic computer science principle, attributed to Sulzer, Reed, and Clark, but it applies so perfectly here. The core idea is that a function, like ensuring something happens exactly once, duplicate suppression, can only be completely and correctly implemented at the endpoints of a communication system, with the application's explicit help and understanding of what exactly once means in its context. Lower levels can help, but can't guarantee it alone.
And I remember reading the perfect example of where this breaks down, duplicate money transfers. Even if TCP ensures no duplicate packets arrive at the server,
Right.
a user retrying a failed HTTP PST for a money transfer, maybe the network timed out after the server processed it, but before the user got the confirmation, can still lead to a duplicate transaction at the application and database level. Why is that so counterintuitive?
Because from the system's perspective lower down, that retry is a new, distinct request arriving from the endpoint,
Hmm.
the browser or app. The standard begin transaction update commit example that we're all taught is actually not sufficient for real banks for precisely this reason. The network delivered the first request, then the second. The database transaction ensures that one of those requests is processed atomically, sure, but it has no way to know that the second request is actually a retry of the first failed one. From the application's point of view, it just sees two separate requests.
So what's the end-to-end solution for this? How do banks or systems that need this guarantee actually deal with it?
The key is to generate a unique request ID at the client, something like a UEID, often called an idempotency key. You pass this ID through all layers of the system right to the database. Then you use a uniqueness constraint in the database, or similar logic, based on this ID to ensure exactly one's execution at the application level.
Ah, so the database rejects the second attempt because it sees the same ID.
Exactly. The big takeaway here is that lower-level reliability features, like TCP or database transactions, are important building blocks, but they are not by themselves sufficient to ensure end-to-end correctness for application semantics. The application itself needs to take these end-to-end measures. It's on you, the application designer, to define and enforce that ultimate correctness.
Okay, that makes sense. This extends to enforcing other constraints too, like uniqueness for usernames or maybe seat bookings. How do we do that effectively in this new log-based, unbundled world we've been discussing?
Right. Strict uniqueness like ensuring only one user can have a specific username, or only one person books seat 7A on a flight, fundamentally requires consensus. You need agreement. Often, this means having a single leader decide the outcome.
Okay.
But in the unbundled database model, with log-based messaging, if the log is partitioned by the value that needs to be unique, like hashing the username to determine the partition, then a stream processor consuming that specific partition can sequentially and deterministically decide which conflicting operation, say 2 attempts to register the same username, came first based on its position in the log for that partition. This allows uniqueness checking to scale by simply increasing partitions. You're leveraging the ordered log within each partition to enforce order for related operations.
And what about more complex multi-partition transactions like that money transfer example, debiting one account, crediting another, which might live on different partitions? Can we achieve exactly once correctness without resorting to those tricky distributed transactions?
Yes, and it's quite an elegant pattern. You first log the entire intent of the transaction atomically as a single message to your central log. This message contains all the details, debit account, credit account, amount, and that crucial end-to-end request ID.
Okay, log the request first.
Log the request first. Then, stream processors, reading from that log, derive and apply the specific debit and credit instructions to the different account partitions. They use that end-to-end request ID within each partition processing step to deduplicate. So if the processor restarts or the message is delivered twice, it only applies the debit or credit once per partition.
Clever.
This breaks down a complex multi-step operation into simpler, idempotent steps processed via the log, avoiding the overhead and fault tolerance issues of traditional distributed transactions like 2PC or XA.
This leads us to a crucial distinction that's really insightful: timeliness versus integrity. What's the core difference between these two ideas when we talk about data consistency?
Okay, timeliness basically means users observe an up-to-date state. Violations are what we often call eventual consistency. The data might be slightly stale for a moment, they're temporary, maybe annoying, but usually fixable by simply waiting a moment for things to synchronize.
Like waiting for a social media post to appear everywhere.
Exactly. Integrity, on the other hand, is the absence of actual corruption. No data loss, no contradictory data, balances add up, constraints are met. Violations of integrity are what might be called perpetual inconsistency. They're permanent and potentially catastrophic, requiring explicit detection and repair.
And the distinction is so important because the insight is, Integrity is much more important than timeliness. Is that fair to say?
I think it absolutely is
Yeah.
in most cases. Think about your credit card statement again. A 24-hour lag on a transaction appearing is a timeliness issue. Annoying perhaps, but pretty normal.
Mm.
But if the final balance on your statement isn't equal to the sum of all the listed transactions, that's an integrity violation, and that's catastrophic. You'd lose all trust. Event-based data flow systems, being asynchronous, inherently might have weaker timeliness guarantees in some ways compared to, say, a single, strongly consistent database. But integrity is, in fact, central to their design through mechanisms like exactly once message processing semantics and idempotent operations. They often achieve strong integrity without the high coordination cost and fragility of distributed transactions. They effectively decouple the concerns, letting you prioritize integrity.
What about the need for really strict immediate constraints, though? Do we always need that instant check for things like uniqueness?
Well, the research in real-world practice suggests that many applications are actually fine with loose constraints that might be temporarily violated and then perhaps fix up later, asynchronously. Think about airlines overbooking flights slightly, or e-commerce sites occasionally selling an item that just went out of stock.
Yeah, that happens.
Compensating transactions like issuing a refund or an apology voucher.
Hmm.
And workflows to handle these exceptions are often already needed for real-world business scenarios, regardless of your system's strictness. Accepting slightly looser constraints upfront can enable coordination-avoiding data systems that prioritize overall integrity and performance availability, even if it means weaker, immediate timeliness or temporary constraint violations. It's about finding that practical sweet spot.
This next topic is a bit uncomfortable to talk about, maybe, but it's crucial. We often design and build systems assuming a level of perfection, fault-free hardware, bug-free software. But the uncomfortable truth is, as the material says, it is more a question of probabilities. Data corruption is pretty much inevitable sooner or later.
It's definitely the elephant in the room for many systems. We're talking about things like random bit flips in memory cosmic rays, hardware glitches, which are rare per bit, but happen surprisingly often when you have massive amounts of RAM running 24/7.
Right, scale matters.
Scale matters. There are even security issues like rowhammer attacks that can deliberately flip bits in otherwise physically faultless memory. And beyond hardware, we've seen subtle bugs even in robust and well-regarded databases like MySQL and PostgreSQL, failing occasionally to maintain uniqueness constraints or provide true serializable isolation under certain edge cases.
Wow, even the big ones.
Even the big ones. And application code, of course, has far more bugs typically. It's really not a matter of if corruption or inconsistency might happen, but when and how you'll detect it.
And the consequence of this blind trust we often place in our underlying systems. What happens if we just assume everything's okay?
Well, ACID consistency, for example, fundamentally assumes bug-free transactions defining the integrity rules. If applications misuse database features or simply contain bugs that write nonsensical data, database-level integrity isn't guaranteed, even with the strongest isolation. Many systems operate on this blind trust, especially perhaps with less mature NoSQL technologies that might lack strong built-in audit mechanisms or cross-checks. We can't just cross our fingers and hope for the best. Hope isn't a viable engineering strategy.
So what's the real solution to uncovering this, well, inevitable corruption? How do the big players, the hyperscalers, deal with it?
The only way to truly find out about silent corruption or integrity violations is auditing. And not just auditing in the financial sense, but technical auditing for all data systems. Think about large-scale storage systems like HDFS or Amazon S3. They don't fully trust their disks. They are constantly in the background reading back files and comparing checksums or comparing them to other replicas. They actively verify.
And this leads to some absolutely crucial advice for you, the listener, right? Something practical everyone managing data should be doing.
Yes, absolutely. You should always try restoring from your backups periodically to confirm they actually work and contain what you think they contain. Don't just blindly trust that your backup process is working perfectly. Test it. We need to foster a much stronger culture of verification, building more self-validating or self-auditing systems that constantly check their own integrity end to end if possible.
How does this focus on auditing and verification tie back into the data flow and derived data design we've been discussing? Does that model help?
It can help significantly. Event-based systems, with their immutable events and deterministic derivation functions, offer potentially much better auditability. You can, in theory, simply rerun the batch and stream processors on the historical event log to regenerate derived state and compare it against the current state to check for discrepancies.
Oh, like recalculating the spreadsheet.
Exactly. Or even use concepts like time travel debugging to go back and see exactly what sequence of events led to a particular state. And that end-to-end argument we discussed for correctness. It applies perfectly to auditing, too. Integrity checks are most powerful when done end-to-end, as this implicitly verifies all the components, disks, networks, services, algorithms along the data path. This builds increased confidence and perhaps counterintuitively allows you to move faster in the long run because you have more trust in your system's checks and balances.
It sounds like there are also some really promising tools emerging in this space to help us with this verification, maybe using cryptography.
Absolutely. Cryptographic tools, like Merkle trees, which you see used in things like certificate transparency logs and distributed ledgers or blockchains like Bitcoin, are exploring ways to cryptographically prove system integrity in a verifiable way. It's a truly exciting area for the future of data verification, potentially bringing a whole new level of trust and transparency to complex distributed systems.
This entire deep dive, all these technical details about logs and streams and correctness, has really been building towards something much bigger than just technical solutions. It's about doing the right thing, the ethical imperative behind building these incredibly powerful systems.
This is, I think, truly the most important part of the discussion. Every system we build, every piece of software, has consequences in the real world, intended and unintended. As engineers, as developers, as designers, we have a profound responsibility, I believe, to carefully consider those consequences
Yeah.
and to consciously decide what kind of world we want to live in, what kind of impact we want to have.
Yeah.
We often talk about data very abstractly, records and fields, but we must never forget that many, many data sets are about people, their lives, their behaviors, their characteristics. We must treat such data with humanity and respect.
Let's talk about predictive analytics specifically. It holds so much promise, obviously, but also carries real peril, doesn't it?
It's a classic dual-use technology. On one hand, predicting weather patterns or the spread of diseases is clearly beneficial to society. But it's an entirely different story when predictive analytics directly affect individual people's lives. Things like assessing reoffending risk for sentencing, predicting loan defaults, or flagging insurance claims for fraud investigation.
Right.
This can inadvertently lead to what's been called an algorithmic prison, where people can be systematically excluded or disadvantaged based on statistical correlations, often without clear proof of individual wrongdoing or even a meaningful chance of appeal. That's a potentially huge constraint on an individual's freedom and opportunity.
And the risk of bias and discrimination baked into these systems is huge, isn't it? Because we feed them data from the past, and the past often contains historical biases and inequalities.
Precisely. If the input data reflects societal biases, and most historical data does, to some extent the algorithm will almost certainly learn and likely amplify that bias,
Yeah.
as one expert memorably puts it. Machine learning is like money laundering for bias. If we want the future to be better than the past, we need human moral imagination, something algorithms simply don't possess. Data and models should be our tools to build a better future, not our masters dictating a biased one.
This raises critical questions of responsibility and accountability. If an algorithm makes a mistake, maybe denies someone a loan unfairly, who's accountable?
That's a massive legal and ethical challenge right now. Explaining opaque machine learning decisions, especially from complex models, in a legal context or even just to the affected individual is incredibly difficult, sometimes impossible. Algorithms often operate on correlations and stereotypes derived from the data, making individual recourse almost impossible if a decision is wrong due to erroneous data or a learned bias. A blind belief in the supremacy of data for making decisions is not only delusional, it is positively dangerous.
And then there are feedback loops. Beyond just recommendation systems creating echo chambers online, there are more dangerous, self-reinforcing loops that can be really insidious in the real world.
Absolutely.
Yeah.
Like the example given, a bad credit score prediction might lead to someone being unable to get a loan for a car, which makes it harder to get to a job, leading to unemployment, which further worsens their financial situation and thus their predicted score, creating these downward spirals, often hidden behind a camouflage of mathematical rigor and objectivity.
Yeah.
These are often unforeseen consequences, and we need to think about the entire system, including the human interactions and societal structures around the algorithm, to understand their full potential impact. It's a complex dance between algorithms and human behavior.
The rise of surveillance, especially around privacy and tracking, is equally stark and maybe even more pervasive.
It really highlights a core conflict in much of the modern internet economy. If a service is funded primarily by advertising, then the advertisers are the actual customers, and the user's interests, particularly their privacy, naturally tend to take second place. The user essentially becomes the product. Their attention and data are what's being sold. One interesting, if polemic, thought experiment mentioned is to just mentally swap the word data for surveillance in common tech company phrases like, our surveillance scientists use advanced analytics.
Oh, wow. Yeah.
It really reveals the sinister connotations, doesn't it? It
Yeah.
forces us to confront what's actually happening.
And it feels like we've collectively, almost accidentally, built the greatest mass surveillance infrastructure the world has ever seen with our smartphones, smart TVs, web browsing, IoT devices.
It's incredible. And what's particularly interesting is how users often voluntarily, even enthusiastically, adopt this technology, often not fully realizing the extent of the data collection or who it's being collected by, usually corporations, not just governments, though governments often want access later.
And the I've got nothing to hide argument often comes up here. How is that challenged?
It's challenged critically because not everyone is privileged enough to truly have nothing to fear from surveillance. Tracking can profoundly impact things like insurance rates, employment opportunities, loan applications, and the data collected can be incredibly intimate. Think health data from wearables, location history, even potentially inferring what you're typing from smartwatch sensors. It's a level of pervasive, often opaque tracking that's historically unprecedented.
What about consent? We all click agree to those long privacy policies. Is that really meaningful consent in this context?
Well, the argument presented is that users often lack true knowledge or understanding of the data processing because privacy policies, let's be honest, are often designed to obscure more than they reveal. They're legal documents, not clear explanations. And consent isn't truly free if using a service is almost essential for basic social or professional participation. Think about services like Google for search or major social networks for connection. This can lead to what feels like inescapable surveillance. Privacy, it's argued quite compellingly, isn't just about secrecy. It's the freedom to choose what to reveal about oneself. Surveillance fundamentally transfers this decision right from the individual to the data collector, who then exercises your privacy right, often in ways designed to maximize their own profit or objectives. This large-scale transfer of privacy rights, it's historically unprecedented.
It's clear that data is power in the modern economy. It's considered a core asset, valuing startups often by their eyeballs, essentially, their surveillance capabilities and the data they hold.
But it's also been described quite pointedly as a toxic asset or hazardous material. Why? Because governments inevitably want access to it, companies go bankrupt and sell it off, and data breaches happen with disconcerting regularity. We must consider not just the current government, but all possible future governments, because, as the text warns, it is poor civic hygiene to install technologies that could someday facilitate a police state. History teaches us that power structures change. As Hesen famously said, knowledge is power, and to scrutinize others while avoiding scrutiny oneself is one of the most important forms of power. Surveillance grants that power asymmetry.
This reminds me of the powerful parallel drawn in the source material to the Industrial Revolution. It feels incredibly apt for our current moment, doesn't it?
It really does. The information age is uncannily like the Industrial Revolution. It brought incredible progress, innovation, wealth creation, absolutely. But it also brought profound, initially unforeseen problems.
Right.
Pollution, dangerous working conditions, child labor, massive social upheaval, and the direct quote used is stark and memorable. Data is the pollution problem of the information age, and protecting privacy is the environmental challenge. It suggests our grandchildren will look back at us at this specific moment in history and judge us on how we address the challenge of mass data collection and potential misuse. That's a powerful mirror to hold up to ourselves, I think.
So what's the path forward here? Legislation like GDPR in Europe certainly aims to help, but it often seems to conflict with the prevailing big data philosophy of maximizing collection for unforeseen future purposes.
This really calls for a profound culture shift within the tech industry itself. We need to move beyond seeing users as mere metrics on a dashboard or resources to be extracted. We need to start consistently treating them as humans who deserve respect, dignity, and agency over their own lives and information. We must, as an industry, self-regulate our data collection and processing practices much more thoughtfully, aiming to build genuine trust, not just compliance, and truly educate end users about what's happening with their data in clear, understandable terms. The ultimate goal should be to empower individuals to maintain their privacy, that is, their control over their own data, and not steal that control from them through opaque or coercive surveillance. Otherwise, we risk a classic tragedy of the commons, where everyone's privacy is gradually eroded for the short-term gain of a few actors.
Are there technical solutions too?
Yes, alongside the cultural shift, there are technical approaches, things like robust data minimization, purging data when it's no longer strictly needed for the purpose it was collected for, better anonymization techniques, although those are notoriously difficult to get right, more advanced ideas around cryptographic access control, and perhaps even privacy-preserving computation. But ultimately, the technology serves the culture and the business model. It requires fundamental changes in culture and attitude within the industry to prioritize user well-being.
Wow. What a journey this has been. We've gone from tackling the really intricate technical complexities of data integration, keeping systems consistent, ensuring correctness in these incredibly complex, fault-prone environments, all the way to confronting these profound ethical implications of the data we collect and the systems we build upon it.
We've gained insights into how data flows, how to unify batch and stream processing, how to verify integrity, even when we know errors are inevitable. We've learned about building systems that are robust, scalable, and correct from an engineering perspective.
And as we wrap up this deep dive, that final crucial question really remains, building on everything we've explored, are we building systems that are truly beneficial to humanity, beyond just being technically clever or profitable? What kind of world are we actually contributing to with every line of code we write, every data point we collect, every algorithm we deploy? And how will our actions today, right now, in this transformative information age, be judged by future generations as they inevitably look back on what we've built? Something to really think about.